My name is Kousuke Murate from Nagoya University, Japan. Today, I'll talk about non-destructive inspection using térahertz spectroscopy, térahertz parametric source. My affiliation is Nagoya University, but last year, I had stayed at ETS for 6 months from August 2017 to February 2018 as research internship in Francois Blanchard Lab. It was so nice experience for me. So now I'm really like ETS and Montreal now. So today I'm so happy to come back here and give a talk. Thank you, Francois, to invite me to here. Okay, I'll start my slide. I'm from Nagoya in Japan. The Nagoya City is located. Nagoya City is Japan's fourth largest city, where locates around the central part between Tokyo and Osaka. It is near from Kyoto. We can go to Kyoto using bullet train about 30 minutes. In Nagoya, there is many big buildings, nice city park, and also Nagoya Castle. It is nice city to live, I think, but it is, I think it is not good for tourists. It means there is no good spot for sightseeing except Nagoya Castle. So if you are planning to go to Nagoya, I don't recommend you. But on the other hand, Nagoya is known as one of the largest industrial area in Japan. There are many big companies in Nagoya, especially there is a headquarters of Toyota Motor Manufacturing Company. And also there is a aircraft factory of Mitsubishi Heavy Industries. Nagoya University is located in such an industrial area, so it has nice engineering and science department, which turns out 6 Nobel laureates in this century, as shown here. Especially Hiroshi Amano, who got the Nobel Prize in Physics in 2040 for investigating the blue LED, is belonging to our electric engineering department. This shows a member of Kawase laboratory. Our laboratory is belonging to electric engineering. And professor is Kodo Kawase, who is a pioneer of térahertz field, and lecturer is Keita Kea, who is researching about methane hydrate using térahertz wave. And assistant professor is me. And we also have the 1 PhD course student, 11 master course student, and 6 undergraduate students. We recommend students to go to the PhD course, but unfortunately, most of students don't go to the PhD course because they can easily find a nice job like Toyota or some other companies in Aichi. So we are looking for new PhD course student, but we can't get new one. So if you are interested in our research over Japan, we welcome you a visit to our laboratory. Okay, let's move on to the introduction of térahertz wave. Maybe Francois is also talked about this, but I'll introduce a little bit again in English. Térahertz wave is one of the electromagnetic waves lies between radio waves and light waves and shares the characteristics of both. It has good characteristics like this, like it has many materials are transparent in this region and safety on human body, and many chemicals have fingerprints in this region. So we can identify region for some chemicals using this Ice Tpg. Using this térahertz wave. So térahertz wave can be used for a wide variety of applications. Using térahertz wave, it is possible to image many samples which were difficult in the past. Like, for example, we can image the soft materials like shrimp and red peppers, and also we can image the IC card, and we can detect the illicit drugs in the mail. Moreover, we can get a 3D image of figures. It is Japanese traditional figure, and this is a peel structure of apple, and this is a carbon inside the diesel engine filter. However, térahertz wave is still fundamental research phase because there aren't high-power térahertz wave emitter and sensitive térahertz wave detector. This figure is here also, already shows France, but I show it again. This is the output power of electromagnetic wave sources. This side is a right wave source and a radio wave source, and this side is a right wave source. However, there are not high power source between 1 to 3 terahertz region. We call this terahertz gap, and we are trying to develop the high power terahertz wave source which fill up this gap. And many researchers in Japan also trying to develop such kind of the high power terahertz wave source. So before my talk, I'll little bit introduce about the terahertz wave research in Japan. This is a terahertz parametric source and detector from, by Dr. Minamide from Riken. Recently, he achieved more than 50 kilowatt peak power output and sensitive terahertz wave detection. We are also researching about same things. It means a terahertz parametric source. So sometimes he becomes a rival, but sometimes he becomes a good collaborator for us. And this is a Cherenkov phase match nonlinear optical terahertz detection, non-collinear phase matching optical terahertz detection by Professor Tani from Fukui University. Generally, Cherenkov phase matching is used for terahertz wave generation, but he used this phase matching method for terahertz wave detection, and he got a nice data recently. This is a resonant tunneling diode, RTD, by Professor Asada from Tokyo Institute of Technology. RTD is terahertz oscillators, which using electron devices. So it means it doesn't need a laser, and his RTD can emit up to 1.96 terahertz. And next, I'll talk about the terahertz wave application research in Japan. One of the important terahertz application is terahertz wireless communication. And Professor Nagatsuma from Osaka University is a pioneer of terahertz wireless communication. Recently, he achieved 48 gigabit per sec using 300 gigahertz. And Professor Tanaka from Kyoto University is researching about extreme nonlinear terahertz optics. To research such kind of nonlinear terahertz optics, he is also studying high-interest terahertz source and some measurement scheme for nonlinear optics. And this shows a laser terahertz emission microscopy by Professor Tonouchi from Osaka University. Using this scheme, it can locate the electrical failure in LSI, as shown here. And there are also many terahertz products from Japanese companies. This is a terahertz camera from NEC, and this is a broadband and high-speed terahertz measurement system from Advantest, and this is a useful continuous wave terahertz wave source from NTT Electronics, and this is a photoconductive antenna and a microchip neodymium YAG laser, which is a pump source for terahertz parametric generation from Hamamatsu. And this shows a mail screening system by Shibuya. They combined X-ray unit, visible camera, and terahertz wave to find illicit drug in the mail. Although this system was developed more than 10 years ago, but they couldn't sell it because the dynamic range of terahertz wave unit was not so good at that time. But they still continue researching such kind of system by collaborating with our group. And this shows the inspection of car painting by Imura and Aishin. Those two companies are belonging to the Toyota group. They use a terahertz time domain spectroscopic system with dust crystal. It can generate ultra-short terahertz pulse which pass through the car painting. And using such a ultra-short pulse, they can measure thin painting layer by detecting the echo from each layer, as shown here. Okay, let's move on to the main topic of my talk. It is a terahertz research in Kawase laboratory. Our laboratory is belonging to engineering department, so our objective is the development of the high-performance terahertz wave measurement system to achieve the industrial application. To achieve such objective, we are researching about mainly two topics. One is a térahertz wave parametric generator, and the other is a térahertz TDS using nonlinear crystal waveguide. Okay, I'll start with a térahertz wave parametric generator. Firstly, I'll introduce about high dynamic range térahertz spectroscopic system. This is an introduction of our parametric source. We are studying about injection shielded térahertz wave parametric generator, which we call ISTPG. ISTPG generates high power térahertz wave from two wavelengths near infrared light. Recently, the output peak power of ISTPG reached more than 50 kilowatt with less than 4 gigahertz line width, and tunable range reached 0.4 to 5 terahertz. Moreover, ISTPG can be also used for terahertz wave detection. Sensitive detection is possible by wavelength conversion of terahertz wave to near infrared light. The sensitivity of this method is better than 4 Kelvin silicon bolometer. As shown here, ISTPG can be used for both of emission and detection. So we can develop the high performance terahertz wave spectrometer using this ISTPG. Next, I'll talk about the principle of terahertz wave emission by ISTPG. This shows a terahertz wave parametric generator, which we call TPG. When the intense palm beam is incident to the lithium niobate crystal, the energy of palm beam was divided to the near infrared line and terahertz wave via stimulated polariton scattering. The output of such system was low power and broadband. On the other hand, when a single frequency seed beam are injected to the crystal with palm beam, a high power and single longitudinal mode terahertz wave is generated. This is injection shielded terahertz wave parametric generator, which we call ISTPG. In ISTPG, the terahertz wave of wide tunability was realized by varying the wavelength and injection angle of seed beam. So this is a tunable source. And also, the principle of ISTPG also can be used for terahertz wave detection. Now, the sensitivity of existing room temperature terahertz wave detectors are poor. So, in this work, we converted the terahertz wave to near infrared light based on frequency up conversion method. Since this method is based on ISTPG, by shielding the terahertz wave instead of light, the corresponding detection idler beams are generated. And then we measure such kind of the detection idler beam using infrared detector. Since we can easily access sensitive infrared detector, sensitive terahertz wave detection is possible. And at that time, the detection idler beam angle is changed with frequency because of non-collinear phase matching condition. Therefore, we can measure the frequency and power using CCD camera at the same time, as shown here. This is a detection beam of 1.5 terahertz, 1.7 terahertz, and 1.9 terahertz. Coordinates shows the frequency, and we can also measure the power at the same time, as shown here. We developed the terahertz wave spectroscopic system using ISTPG, as explained in previous slide. We used ISTPG for both of emission and detection. We use a microchip neodymium YAG laser for pump source and external cavity laser diode for seed source. As a result of inputting those lasers to the lithium niobate crystal, coherent single frequency and high power terahertz wave is generated. And then the generated terahertz waves were focused onto another crystal for detection after pass-through a sample, and up converted to the detection beam, which is detected using pyroelectric detector. This is a photo of our setup. The blue line is a palm beam optical path, and green line shows the optical path of seed beam. Terahertz wave is generated at this crystal, and it is passed through the air, and here is a detection crystal, and up converted to the detection beam, and measure it using pyroelectric detector around here. This shows a spectrum of ISTPG spectrometer. We measure the spectrum with different attenuation factor, which is varied by terahertz wave attenuator in the terahertz path in order to measure the dynamic range, as shown here. It is those lines means different terahertz wave attenuation factor. From this result, we confirm the dynamic range of more than 70 decibel. Next, I'll talk about the tunability enhancement of the ISTPG. This shows a comparison of ISTPGs between 2002 and 2014. The output peak power of ISTPG was improved drastically. Compared with 2002, the output peak power reached more, compared to the, in 2002, the output peak power was only 200 milliwatt, but it reached more than 50 kilowatt in 2014. It was improved drastically. On the other hand, tuning range was not so much improved. In 2002, it was 0.6 to 2.5 terahertz, and it reached to 3 terahertz in 2014. It was improved only 0.5 terahertz. So in this work, we tried to improve this tuning range, more high-frequency region. There was a limitation in high-frequency terahertz wave generation in our previous work. It was a high absorption loss in the crystal. These figures show the terahertz wave emission part of ISTPG. In our previous setup, inside a lithium-ion crystal, a terahertz wave is generated across the pump beam via excitation from the pump pulse. However, in high-frequency region, it doesn't amplify well because of the absorption loss. On the other hand, in improved setup, we inclined the lithium-ion crystal a little bit so that a portion of the pump beam was internally reflected as a terahertz wave exit surface. In this configuration, it became easier for high-frequency terahertz wave to reach to the terahertz wave exit surface. So we can improve the tuning range, as shown here. This orange line shows the tuning range of previous work. It was 1 to 3 terahertz. But on the other hand, the blue line shows the improved tuning range. It reached 0.6 to 5 terahertz. The parameter of tuning range was improved about 2 terahertz by inclining the crystal. Okay, next I'll talk about the real-time terahertz spectroscopic system using Ice Tpg. As I explained in previous slides, we achieved the ISTPG spectrometer with high dynamic range. However, ISTPG spectrometer requires long measurement time because ISTPG is a tunable source and emits only one wavelength per pulse. So we need to tuning it to get the spectrum. On the other hand, in this work, we try to develop multi-wavelength ISTPG. When the ISTPG generates multi-wavelength terahertz wave, there is no need to change the wavelength. So it is possible to shorten the measurement time and measure the sample in one pulse using this system. This is a principle of multi-wavelength terahertz wave emission by ISTPG. In single frequency generation in conventional ISTPG, we input the single frequency seed beam. On the other hand, multi-wavelength seed beams are injected to the lithium-ion crystal. Multi-wavelength terahertz waves were generated. This is multi-wavelength ISTPG, which we used in this study. And terahertz wave detection methods are also used for multi-wavelength detection. When we input the multi-wavelength terahertz wave to the detection crystal, the generation angle of detection beams are changed with each wavelength and a phase matching condition. So multi-wavelength terahertz waves can be detected spatially separately. This shows the experimental setup for 5 wavelength terahertz parametric generation and detection. We use a microchip laser for the pump beam, and we use 5 external cavity laser diodes for the 5 wavelength seed beams. As a result of input of pump beam and 5 wavelength seed beams to the lithium-ion crystal, 5 wavelength terahertz waves were generated. And then it was detected based on frequency up conversion method in the lithium-ion crystal and measures the detection hydro beams using camera. This shows measured detection hydro beams, which are converted from 5 wavelength terahertz wave. Using this method, intensity and wavelengths of terahertz wave were obtained at the same time, as shown here. And we confirm that we achieved the 5 wavelengths generation and also detection, as shown here. And we also measure the dynamic range of the system. This figure shows the detection beam output as a function of frequency when we vary the attenuation factor of terahertz wave. From this figure, we confirm the dynamic range of more than 50 decibel. Using such a system, we measure the saccharide pellets as shown here. This graph shows the reference transmittance spectrum which we got using terahertz TDS system. We set 5 frequencies of 1.36 to 2 terahertz in multi-wavelength generation to match the absorption spectrum. This video shows the measurement result of detection idler beams when we inserted the maltose and lactose to the terahertz path. When we inserted the maltose, we confirmed the attenuation of the 1.64 and 2 terahertz as same as the reference spectrum. And when we inserted lactose, we also confirmed the attenuation of 1.36 and 1.83 terahertz as same as the reference spectrum. As shown in this result, we can measure the sample information in real time using this system. From that result, we calculated the transmittance of each saccharide as shown here. We confirmed that the transmittance which we got using multi-wavelength Ice Tpg is almost same as what we got using terahertz TDS. So it means our system is possible to measure the absorption spectrum in one shot, and our system will be a real-time measurement system in the future. Next, I'll talk about the terahertz parametric amplifier. In terahertz research field, 4 Kelvin silicon borometer is still used for detection of weak terahertz wave. 4 Kelvin silicon borometer needs a liquid helium, so it is difficult to handle. So in this work, we try to develop terahertz wave parametric amplifier to detect such kind of weak terahertz wave using a room temperature detector. This figure shows the principle of terahertz wave parametric amplification. It is almost same as terahertz wave detection, but in this configuration, terahertz wave was amplified by interaction with pan beam, and it is generated at the end of the crystal. We firstly achieved this terahertz wave parametric amplification in 2014. This is a result at that time. The maximum amplification factor was 50 dB, and at frequency is 1.6 terahertz. However, at that time, it was difficult to amplify weak terahertz wave input. When the terahertz wave input was strong, the terahertz wave amplified without limitation, and a single frequency terahertz wave was generated, as shown here. On the other hand, terahertz wave input became weak. A broadband terahertz wave generation, which we call TPG, is generated, and it becomes a noise. So we can't get enough amplified terahertz wave signal. So it is necessary to suppress this broadband generation and increase the generation gain. And such a problem was particularly pronounced in low-frequency terahertz region. This graph shows, figure shows frequency dependence of maximum amplification factor in 2014. In theta frequency region, it was amplified well. On the other hand, in low frequency region, it means 1 terahertz was amplified only 1,000 times. It is because parametric amplification gain in low frequency region is lower than high frequency region. So when we input the low frequency and weak terahertz wave input to the receiving crystal, we can't get enough terahertz wave amplified terahertz wave signal. To solve such a problem, we improve the amplification setup. In our previous setup, when we input the weak terahertz wave, most of the energy was used for broadband terahertz generation. So weak terahertz wave was not amplified well. On the other hand, in this new scheme, we separate the amplifier to the preamplifier and the main amplifier. In preamplifier part, terahertz wave was converted into the near-infrared light based on frequency up conversion method. And at that time, broadband light and single frequency beam are specially separated due to the non-collinear phase matching condition. So we can eliminate the broadband light using the iris at here, and only single frequency beam can be amplified on the main amplifier. Using this setup, we can decrease the noise, and amplification gain was increased. This is a result of such kind of the new setup. This shows the input-output characteristics of the amplifier. Red dot shows the result of this time, and orange dot shows the result in our previous work. When we look at the previous work, the minimum input was 58 femtojoule. On the other hand, in this setup, we can amplify 90 zeptojoule input. It is 60 decibel lower input energy than before. From that result, we calculated the amplification factor as shown here. The maximum amplification factor increased about 65 decibel from previous setup, and it reached more than 90 dB. It means 94 decibel. As shown here, terahertz wave of 100 zeptojoule or less is amplified more than 2 billion times. Okay, next I'll talk about the applications using Ice Tpg. It is a mail inspection system and 3D terahertz tomography. In terahertz range, 0.5 to 3 terahertz range is useful for inspections, because many chemicals have fingerprints above 0.5 terahertz, and many materials are transparent below 3 terahertz. X-ray also has transparent characteristics, but many chemicals doesn't have the fingerprints in this situation. So only terahertz wave can see through the material and tell kinds of drugs. And Ice Tpg is suitable for non-destructive inspection system, because illicit drugs are packed in some envelopes like this, and terahertz wave is scattered, refracted, and multiple reflected by those envelopes as shown here. So when we use terahertz time domain spectroscopy system, it is difficult to detect such a scattered, reflected, and multiple reflected terahertz waves, because detection area of PCA is very small. It means less than 10 micrometer. On the other hand, Ice Tpg can easily detect the scattered, refracted, and multiple reflected terahertz waves, because detection area is 100 times larger than photoconductive antenna. It is almost 5 millimeter. So we use this system to see the illicit drug in the mail. We have firstly demonstrated terahertz spectroscopic imaging in 2003 as shown here, introducing component spatial pattern analysis. The spatial distribution of the targets were obtained from terahertz multispectral images using absorption spectra measured using TPO. However, at that time, the dynamic range of TPO system used in 2003 was as low as 4 orders. So we can see through only 0.1 millimeter thick envelope. It is very thin. But now we have more than 7 orders of dynamic range, so we can see through more thick envelopes. We use the terahertz Ice Tpg transmittance spectroscopic system for mail inspections. This system is same as I explained in previous slides. The dynamic range was more than 70 decibel, and spectral bandwidth was 1 to 2.6 terahertz. Spectral flat range was 1.2 to 2.2 terahertz. This is a measured sample. We measured 3 saccharides, that is lactose, maltose, glucose, and fructose inside the 23 millimeter thick envelopes, which consists of EMS envelope, corrugated cardboard, and bubble wrap. This is a side photo of the sample. And this is a result of detection of reagents in thick envelopes. From the top, the spatial distribution of maltose, glucose, and fructose. The saccharides have been clearly distinguished even in the case where the target was hidden in 23 mm thick envelope. And also, we achieved the 3D terahertz computed tomography of plastics as shown here. This is a consent plug cover, this is a nylon connector, and this is a cigar socket, and this is a test sample for internal defect inspection. Ice Tpg has high dynamic range around 1 terahertz, and the detection area is larger than other systems. So it is possible to measure these high absorbed samples, which was not be able to measure with other systems. Okay, from now I'll talk about the next topic of terahertz time domain spectroscopy using nonlinear crystal waveguide. This shows the terahertz emitter for terahertz TDS. There are two major methods to generate terahertz wave for terahertz TDS. One is photoconductive antenna, and the other is nonlinear crystal. The photoconductive antenna is easy to handle, so it is very widely used in all over the world. However, photoconductive antenna has this demerit. It is low damage threshold, and terahertz wave output is easy to saturate with input pump beam. On the other hand, nonlinear crystal has high damage threshold, and terahertz wave output is proportional to the square of input. So in this work, we introduced this nonlinear crystal for high-efficient terahertz wave generation. To generate the terahertz wave using nonlinear crystal, we need to consider Cherenkov phase matching. Cherenkov phase matching is a popular phenomenon that can be observed in daily life. Franz already talked with both, but now I talked with duck, and it is slower and high-speed jet aircraft. It is a very fast one, but there are also same phenomena, Cherenkov phase matching, and it is also observed in terahertz wave generation, as shown here. Refractive index between palm beam and terahertz wave is not same. It means the speed of terahertz wave is slower than palm beam inside the crystal. So terahertz wave generated to the direction fits the phase of the spherical waves overlap as shown here. This is the Cherenkov phase match terahertz wave generation. However, the real palm beam has a finite diameter. So phase of the palm beam from bottom and top of the phase of the palm beam, phase of the terahertz wave from bottom and top of the palm beam are different. So this phase mismatch reduces the terahertz wave efficiency. Phase is mismatch. So in this work, we make a waveguide crystal. It means a waveguide for palm beam in order to trap the palm beam in the small crystal inside the small size crystal and make the beam size as small as possible. This is a real photo of the lithium niobate waveguide. The size was very small. It was a micrometer on that, and length was 10 millimeter. This is a side photo of the lithium niobate waveguide. We put the half-cone silicon lens to couple the terahertz wave to the air at here. This is an experimental setup for terahertz wave generation. This is an experimental setup for terahertz wave generation. We use a femtosecond fiber laser, which has these characteristics for palm beam and probe beam. Terahertz wave is generated at here and detected using bow-tie type photoconductive antenna. This is a result of terahertz wave generation from lithium niobate waveguide. This is time waveform, and this is spectrum. We achieved the dynamic range of 80 dB and bandwidth reached to 7 terahertz. It is relatively good compared with conventional terahertz time domain spectroscopic system. Here is a conclusion. We achieved development of Ice Tpg spectrometer, which has a dynamic range of more than 70 dB, and tunable range was 0.6 to 5 terahertz. Using this system, we achieved these applications. One is a drug detection under thick envelopes, and the other is a 3D computed tomography of plastics. And we also achieved the real-time measurement system. Saccharized pellets were identified in real time by multi-wavelength generation. And this shows the terahertz high-gain terahertz parametric amplifier. Terahertz wave of 100 zeptojoule or less is amplified more than 2 billion times using this new scheme. And we also introduced the terahertz generation from rich waveguide. The dynamic range reached 80 dB and bandwidth was up to 7 terahertz. Here is the acknowledgement. Thank you for your attention.